So, hello everyone. Today I will discuss about the determination of surface tension of solids. So, in the last two lectures, first I discussed the measurement of surface tension of liquid. Then in the last lecture I discussed about the uh, measurement of the contact angle. So, in the last lecture we discussed different method of measuring the contact angle. So, that was the sessile drop method, then plate method. Also we discussed if we are having the porous solid or porous powder, then from that powder we can prepare the powder sample can be prepared in the porous plug, and then we can pass to one in wetting liquid, one is non-wetting liquid, and if we can measure the pressure difference in both the cases, we should be able to measure the water contact angle. Followed by that we discuss what is the equilibrium contact angle, and also we discuss the dynamic contact angle, the advancing and receding contact angle. So, today we will discuss how we can measure the surface energy or surface tension of a solid surface. So, the problem with the solids is we mostly go with the indirect method of the surface tension of solids. So, that anyway we will discuss. Apart from that, we will discuss what are the different methods are available to measure the surface energy or surface tension of solids. Also, we will see few examples particularly based on the contact angle based method to determine the surface energy of solids. Also, we will see how we can measure the adhesion force, and from adhesion force we can calculate the surface tension. So, surface tension of solids. So, there are two key challenges if you go for the surface tension of solids. The first one is, as you remember, the surface tension we say that surface energy or the work done per unit area of the interface. But here what is happening, when the surface area is increased, so the whatever work supplied, it does not appear as the surface free energy. So, this happens because of the property of the solid. So, that one is it is rigid, second thing its elasticity. So, also if you remember, when we are talking about the surface tension of the liquid, we form a drop of the liquid because of the surface tension. Now, if you follow the same protocol for the solids also, so what we can do? We can melt a solid. Once it is melt means it is like a viscous liquid, but here the formation of the shape is not only coming from the cohesive force or surface tension, it is also coming from its elasticity. So, these are the two key challenges when we try to increase the unit area of the interface. All the work supplied does not go or does not reflect the surface free energy. And second thing is, if you are trying to form a particular shape, then this formation of shape is not solely depends on the cohesion energy or the surface tension. So, these are the two key challenges, that is why we cannot follow the similar methods which is used to measure the surface tension of the liquids. So, there are two key challenges, they are arising because of the rigidity, elasticity as well as the plasticity of the solids. So, what are the different options to measure the surface tension of solids? The first one is, as I told, you can melt it. Once you melt it, it means it is looking like a viscous liquid. And it can be treated as a liquid to measure its surface tension. But again the problem, as I told, even it is a viscous liquid, when you try to form a particular shape, it is also carrying its past history, it is also carrying its elasticity apart from the interfacial energy. The next method is the heat of solution. So, if you want to melt it, you want to melt means you want to break the intermolecular interactions, then heat required, it can be correlated with the surface energy or the surface tension. So, for this we take two cases, one is for the coarse crystalline material and second for the fine crystalline material, and we do measure the heat of solution, and based on this we should be able to see if it is coarse and it is fine, there will be certain differences, and that difference indicates or it can be correlated with the surface tension of solids. As I told, if you are let us say energy of vaporization or energy of the melting, or you can say this is a latent heat, it is directly proportional to the self energy into n naught is the Avogadro number, and this self energy is proportional to the pair potential into 12 upon n minus 3. So, C is the constant and sigma is the intermolecular distance to the power n. So, you see if you can measure this latent heat, or you can say we can measure the self energy, then again you should be able to calculate the surface tension of that particular solid. Next method is the abrasion or grinding. Whenever you are going to do some mechanical exercise at the surface, it may be the abrasion, it may be the grinding, then you require the energy, and that energy will also include interfacial energy along with required for its deformation, maybe abrasion or grinding. So, whatever energy you are supplying, it includes both the interfacial work as well as the deformation work. So, in this way also we can calculate the surface energy of solids. The similar method is the, if you want to cleave it, work of cleavage. So, if you want to cleave it means whatever the cohesive energy is there per unit length, that must be overcome during the cleavage, and that energy, the cohesive energy itself reflect the surface tension. Another option is we can just see the solubility. You can put a solid which is soluble in a particular solvent. So, depending on the solubility can be related with its self energy, and self energy is related with the interfacial tension. If you remember the previous lectures, this is a Boltzmann equation where mu I is the self energy, k is the Boltzmann constant, T is the temperature, and x s is the solubility. In fact, we have also did one exercise to see the how the solubility of the NaCl is related with its surface energy. Another method is supercooling of melt. You are having a melt, now you want to cool it down. So, if you are cooling it down, you are bringing it into contact of a liquid. So, it is like a solid liquid interface. It is like a solid liquid interface, and if you are cooling, so during the cooling process also there is a interaction between the molecules from melting to the cooling, and that interaction also includes the interfacial tension or the surface energy. Another method is we can measure the adhesion force. On the surface top layer you can measure the adhesion force, and that force is related with the surface tension or surface energy. And the important method which we usually follow is the you measure the wettability or the contact angle on the surface and try to correlate it with the surface energy using the Young's equation and Dupre equation. So, this is the you can say indirect method, because we are calculating the surface energy by measuring the contact angle data. So, we will discuss this wettability or contact angle method first, then we will also see few examples based on this method how we can calculate the surface tension of solids. Then we will briefly see how we can measure the adhesion force of solids. So, one is the what is adhesion energy before we start. So, if you remember the van der Waals interaction between two planar surface, this is the let us say two planar surface, distance between them is d. So, the work of adhesion is A divided by 12 pi d square, where A is the Hamaker constant, which is defined as pi square c into rho square, where c is the London constant and rho is the number density. So, if you know the work of adhesion, so this is like a work of cohesion W11. So, W11, so cohesive energy between two neighboring molecules. Let us say this is between the two planar surface. Now, we want to calculate between the two neighboring molecules. So, here we are replacing d with the d naught. So, the cohesive energy will have the same expression, only we are replacing d with the d naught. Now, the cohesive energy is twice of the surface tension. So, from here we can calculate the surface tension is equal to A upon 24 pi d naught square. So, here we are considering the cohesive between the two layers, or you can say the two internal layers of that particular solid, and distance between them is we are considering d naught. So, in this method, if the adhesion energy we can calculate theoretically, we can calculate the value of surface tension. So, in order to calculate the work of adhesion we can also calculate from after measuring the wettability or the contact angle. So, work of adhesion on the solid interface we can easily measure by putting a drop of liquid, which is forming a angle contact angle theta. So, at the point of contact we are having, it is experiencing three forces or three tensions. One is the between the solid and vapor, other is the liquids and solid, and third interface is between liquid and vapor. So, here there are three interfaces: surface tension of liquid, surface tension of solid, and interfacial tension between solid and liquid. So, work of adhesion is surface tension of liquid plus surface tension of solid minus interfacial tension. So, if you remember, W12 is equal to gamma 1 plus gamma 2 minus gamma 12. Now, we can correlate these three surface tensions or these three interfacial tension using Young's equation. So, Young's equation say cos theta is equal to gamma S V minus gamma S L divided by gamma L V. So, if you combine this Young's equation with the Dupre equation, so it says W S L. So, what you can replace either term. So, it will come in terms of the, I just replace this term gamma S V minus gamma S L is equal to gamma L V cos theta. So, this will be gamma L V plus gamma L V cos theta So, you can take out the gamma LV and cos theta. So, what it says is, if you can measure surface tension of liquid, and theta is the contact angle. So, if you can measure the surface tension of liquid and contact angle, we can calculate the work of adhesion, and from the work of adhesion we can calculate either interfacial tension or the surface tension of the solid. So, what experimentally we need to measure is, we need to measure the surface tension of that particular liquid, which we are using for the contact angle measurement, and of course, that contact angle. From these two data we will be able to calculate the interfacial tension as well as the surface tension of that particular solid. So, Giri, Falco and Goods assume the work of adhesion as a geometric mean of the two surface tensions. So, W12 is equal to twice phi gamma 1 gamma 2 to the power half. So, here phi is a function of the molar volume of 1 and 2, and if this molecular diameters follow the geometrical mean, then its value is 1. And again, if you remember, we discussed the surface tension of a particular solid or liquid have two components. One is the dispersive or non-polar, other is the polar. So, if you write this gamma 1 as gamma 1 polar plus gamma 1 dispersive, similar for the gamma 2. So, this will be W12 equal to 2 phi gamma 1 dispersive, gamma 2 dispersive to the power half plus gamma 1 polar, gamma 2 polar to the power half. So, if you compare the previous equation, that W12 in terms of the contact angle, and here this W12 is coming in terms of the surface tension. So, if you combine this, so this is the value of phi. For alkane its value is 0.55, for aromatic hydrocarbon 0.7, for polar liquids it vary between 0.6 to 9, and for hydrogen bonding compounds its value is 1. So, mostly if you measure the contact angle of water on the surface, we consider its value close to 1. So, we can, as I told, that work of adhesion we can write in terms of surface tension, again the work of adhesion we can write in terms of surface tension. So, from work of adhesion we can also write the interfacial tension, gamma 12 is equal to gamma 1 plus gamma 2 minus W12. We can calculate the interfacial tension between solid and liquid. Now, if you calculate this interfacial tension between solid and liquid, then from easily from the Young's equation we can calculate the liquid vapor is experimentally known, contact angle is known, interfacial tension we calculated from the work of adhesion, then surface tension of solid we can easily calculate from the Young's equation. So, if you combine these two expressions of the work of adhesion, one in terms of the contact angle which is derived from the Young's and Dupré equation, other from the Giri-Falco and Goods equation. So, what it says is gamma LV liquid surface tension we can measure experimentally, contact angle we are measuring experimentally, gamma SV we have to calculate, gamma LV is known, gamma SV polar we have to calculate. So, this is known, this is known, this where this is, so these are known, only these are the two unknown parameters 1 and 2. So, as these are two unknown parameters, so we require minimum 2 equations. So, what it says, we have to measure the contact angle of at least 2 liquids. So, 2 liquids means one liquid will have contact angle theta 1, other will have contact angle theta 2, one liquid will have gamma L 1, its surface tension of the liquid, other will have gamma L 2 surface tension of another liquids. So, if you combine these two equations, so we should be able to calculate now gamma S dispersive plus gamma S polar, and that is equal to the gamma S. So, in this way we will be able to calculate the surface energy of the solid. So, from the work of adhesion we can calculate the interfacial energy, and again using the Young's equation we can calculate the surface energy of the solid. So, I will discuss few examples here. First is, let us say you are having a paraffin wax and you are measuring the contact angle of water, contact angle you are measuring is 111. It means as expected it is a hydrophobic surface, contact angle is more than 90, contact angle is more than 90, it is a hydrophobic surface. And here the surface energy of the solid is 25 and surface energy of liquid is 73. So, we need to determine the interfacial tension, gamma 1 2 and work of adhesion. So, if you apply simply Young's equation, so it says cos theta is equal to gamma S b minus gamma S L divided by gamma L v. So, it says cos theta is equal to gamma S b minus gamma S L divided by gamma L v. So, we can easily calculate value of interfacial tension, that is coming out to be 51 millijoule per meter square. Now, once gamma 1 2 interfacial tension is known, we can calculate the work of adhesion, gamma 1 plus gamma 2 minus gamma 1 2, its value is coming to be 47 millijoule per meter square. Now, we will just see how we can go in either way. We can first calculate the W 1 2, then we can calculate the interfacial tension gamma 1 2. Now, if you remember the Giri-Falco and Goods equation, so it says work of adhesion is the simple geometric mean of the gamma 1 and gamma 2. So, if you take the value of gamma 1, we are taking twice into gamma 1 is 25 into 73 to the power half. Its value is coming out to 85 millijoule per meter square. So, what does it mean is it is not matching with this. So, this is incorrect. So, we have to again expand the gamma 1 and gamma 2 in terms of its polar component and dispersive component. So, if we consider the paraffin we can consider, so gamma 1 is equal to 25 millijoule per meter square and gamma 2 is 73 millijoule per meter square. So, paraffin if we consider purely hydrophobic, so we can say it is having gamma dispersive component is 25. So, its polar component will be 0. Now, for the water its dispersive component is and its polar component. So, if you remember the table we discussed, in case of water the dispersive component is close to 20 and polar component is the 53. So, now if you see here, so the paraffin is not having any polar component. So, this term will be 0. So, now you have to calculate twice into gamma 1 dispersive, that is 25 into water dispersive 20 to the power half. So, now it is coming out to be 45. So, that is very much close to the above value. So, what it says is, although there is a work of adhesion between a solid and liquid, but the interaction is taking place between either polar or non-polar polar. So, if whatever composition is there for your surface, if it is a non-polar, so mostly whatever liquid we are putting, its non-polar component is going to interact. Whole interaction between two surface tension is not taking place. That is why we got the incorrect result here. So, its interaction is taking place depending on the polar and dispersive component of both solid as well as the liquid. Now, here is another example. You are having 4 solids and you are putting the water, you are getting different contact angles 30, 60, 120 and 180 degree. You can consider the surface tension of water as 72. So, now we see, as we are observing different contact angle, means the work of adhesion will be different. So, that we can quickly calculate using the Young-Dupré equation, which says work of adhesion is gamma LV to 1 plus cos theta, and theta value is 30, 60, 120 and 180. So, you can calculate. So, what you are observing is we are getting different value of the work of adhesion. If it is cos 180 means its value is minus 1. So, we are getting 0. So, it says we can calculate the work of adhesion using this Young-Dupré equation. Now, we will combine these two equations, the Goods equation and Young-Dupré equation, to calculate the surface energy of the solid. So, as you remember, if you want to calculate the surface energy of solid, so we need minimum 2 equations, means we have to measure the contact angle of 2 liquids. So, one was water, other liquid was chosen as diiodomethane, and their contact angle was found to be 65 and 34. So, now you have to calculate the polar and dispersive component of that particular surface, and also once this is known, now you want to calculate the contact angle of another liquid, ethylene glycol. So, first we have to measure the we have to know the surface tension or surface energy of liquid, that is given here in the table for water, diiodomethane and ethylene glycol. So, this is the Young-Dupré equation and this is the Goods equation. So, here we have to write the 2 equation, one will be for the water, equation 1 will be for water and equation 2 will be for the diiodomethane. So, this equation is for the water and this equation for the diiodomethane. So, water is having, of course, it is having both the component dispersive as well as the polar component. So, it will have the same equation here, but here if you just see, diiodomethane is having only dispersive component. So, here the polar terms will be 0. So, depending on the value of the polar and dispersive component, we will get the 2 equation, equation number 1 and equation number 2. If you solve these equations, you should be able to get the value of gamma as dispersive and gamma as polar. So, gamma as dispersive is coming 42.49 millijoule per meter square and gamma S polar is 9.45 millijoule per meter square. We will sum them up. So, this will be the total surface tension of that particular solid is 51.93 millijoule per meter square. Now, once this surface energy of solid is known, what we have to again calculate is the contact angle of another liquid. So, here surface energy of liquid is known. So, gamma SB is known, gamma LV is known. So, we can easily calculate the contact angle. For the liquid, gamma LV is known, for the solid gamma SB is known, and their polar and dispersive component are also known. So, in the same equation here the value of cos theta we have to estimate. This is known, these two dispersive component of surface, dispersive component of ethylene glycol, polar component of surface and polar component of ethylene glycol, these are known. So, if you put the value you will get the value of theta, this is coming out to be 29 degree. So, we can see how indirectly by measuring the contact angle of a different liquid on a surface, we can estimate work of adhesion, we can determine the interfacial tension between the solid liquid. Also, we can calculate the surface tension of the solid vapor or surface energy of the solid. So, this is the indirect method we use to calculate by knowing the surface tension of the liquid and measuring the contact angle. So, what we discuss is we discuss the three interface solid, liquid and vapor. So, we discuss like this. This was the solid phase, this was the vapor phase and this is the liquid phase. Now, in actual there can be another three phases, it may not be solid, liquid, vapor. So, in this example we are seeing three different phases. One is the detergent name is given Fatex and DEFA, other phase is the IL and third phase is the glass. So, it is like we are having a detergent phase here and we are having a glass phase here and in between we are having the IL phase, IL and the glass. So, it is not necessary that always we are going to deal with solid, vapor and liquid, you can have any three different mediums. So, here glass, IL and the detergent and the surface tension of the, or you can say interfacial tension of Fatex IL is given, Fatex DEFA IL is given, glassware and IL is given, Fatex and glassware is given, DEFA and glassware is given. So, we want to know that which detergent will be able to remove the IL from the glass. So, if you want to see what is its efficacy, we have to calculate the work of adhesion of the detergent on the glass surface. So, if you remember the work of adhesion between the W12 is gamma 1 plus gamma 2 minus gamma 12. So, here work of adhesion we are going to measure between the glass and IL, that is equal to the surface tension or interfacial tension between glass and detergent plus interfacial tension between detergent and IL minus interfacial tension between glass and IL. This is the same, we are replacing solid with the glass, liquid with IL and vapor with detergent. Now, all value are given here, we can calculate for both the detergents Fatex and DEFA. So, for Fatex it is coming out to be gamma glass and Fatex is 18 plus gamma text and IL is 16 minus gamma glassware and IL is 35, it is coming out to be minus 1. Now, in case of DEFA detergent, we will do the same exercise, it is coming out to be minus 3 millinewton per meter or minus 3 millijoule per meter square. So, as the work of adhesion between the glass and IL is coming out to be negative, it means the detergent is effective, it will be able to remove the IL from the glass surface. Now, if we just compare the value, in case of DEFA it is more negative, it means this particular DEFA detergent is comparably more effective or it has the stronger affinity. So, here what we discussed is we can have any 3 different phases or different mediums, and again we have to repeat the same exercise to calculate the work of adhesion or interfacial tensions or the solid surface tension. So, this was the method based on the contact angle and surface tension of liquid. Now, we will just see if you can experimentally measure the adhesion force. Let us consider the 2 elastic spherical molecules, they are having radii r1 and r2. So, the work of adhesion is given as 3 by 2 pi r w. W is the work of adhesion, F is the adhesion force. Now, R is the R1 into R2 divided by R1 plus R2. Now, this work of adhesion we can write in terms of surface tension or surface energy. So, W is equal to minus 2 gamma. So, it is coming out to be adhesion force is equal to 3 pi r into gamma. So, if we can measure the adhesion force, we can calculate either work of adhesion or the surface energy. How it is done? So, it is calculated by the pulling the sphere with an external force, and if you are pulling the outer layer of a surface, then the force of adhesion is equal to the surface energy or the work of adhesion. So, there are different experimental methods which are applied to measure the adhesion force. So, I will discuss 2 methods here. One is the atomic force microscopy. So, as we know, atomic force microscope has a cantilever, it comes very close to the particular surface, then depending on the attraction forces between the top layer of the solids and the cantilever, it experiences different adhesion forces. So, based on that we will be able to measure the adhesion force, and that is proportional to the K is the spring constant and delta D is the deflection. So, if you put the cantilever, it will experience certain deflection when it comes to the very close to the intermolecular distances, and that force, whatever force, typically what happens when it comes close to the surface, it will have the attractive forces, and if you come further closer, it will have the repulsive forces, if you remember Lennard zone potentials. So, based on that principle, there will be the interaction between the cantilever and the surface, and that adhesion force is proportional to the what is the spring constant and what is the value of deflection. So, if you measure the adhesion force, we can correlate it with the surface tension or the work of adhesion. Another method is the total internal reflection microscopy, TIRM. So, this is used for the weaker interaction, like there are some colloidal particles in the liquid. So, what happens if your intensity of reflected beam, it depends on the distance of the dull particles and the surface. So, if you record the intensity of the reflected beam, then the motion of particles recorded about its mean separation distance between the that solid surface and that particular colloidal particles, and here the accuracy is about, they are coming closer about 5 nanometer. So, what it says, you are having a surface in the colloidal solution. So, colloidal particle will try to come closer to the surface, and when they are coming, there will be the motion of the particles near the surface, and when they are coming, depending on the distance between the surface and particles, the intensity of reflected beam will vary, and based on this we should be able to calculate the work of adhesion or adhesion force. So, these are the two methods. There are few other methods also, like the osmotic pressure methods to measure the adhesion force. So, I conclude here, we can measure the surface tension of solid by various methods, but the key challenges with the solid is their rigid, their elasticity and their plasticity. That is why we cannot treat the, or we cannot apply the same method which we apply for the liquids to measure the surface tension. So, different methods what we discussed is, you can form the melt of that particular solid, it is like a viscous liquid, then we should be able to calculate its surface energy or its heat of solution, or you want to do some mechanical cutting or abrasion or cleavage. Also, if you want to have some solids interaction, means if you want to cool the melted solid, or if you want to see the solubility, if you can put that in the liquid. So, solubility is related with the self energy, or you can say the chemical potential using the Boltzmann equation, then you should be able to calculate the surface tension of the solid. Another method is the adhesion force. If you can measure the adhesion force, as we discussed, you can use the AFM, you can use the TIRM, and most commonly used method is the indirect method, where we measure the contact angle of two different liquids on the surface, solid surface, and depending on the value of the contact angle, we measure the work of adhesion. We can also determine the interfacial tension, and we can calculate the solid vapor interfacial tension or the surface tension or surface energy of a particular solid. Thank you.